with that, I think we could do a round of introductions. It's like a fairly small meeting, and I think we could keep it more on the conversational side. Does that sound good to you, Richard?
Okay, yeah.
Okay. Do you want to kick us off, Richard?
I'm Richard Cullether. I'm a modeling team co-lead. I'm with NASA Goddard with the Global Modeling and Assimilation Office. My other affiliation was with the University of Maryland College Park. Yeah, Arctic reanalyses and seasonal prediction.
Great. Wilbert? Yeah.
My name is Wilbert Weyer. I'm at Los Alamos National Laboratory. I'm co-lead of the modeling team also, but also of the physical oceanography team. I guess we're now called communities of practice. I'm leading the Highlight RASM project for DOE, Department of Energy's Office of Science here at LAL. Thanks.
Perfect. I'll just go ahead and call names as I see them in my screen. So Lorenzo.
Yes, my name is Lorenzo Zampieri, and I'm a postdoc at the National Center for Atmospheric Research in Boulder, Colorado. And yeah, I'm also contributing to the M² Line project, which is multi-scale machine learning in coupled Earth system modeling with many collaborations in the US and France.
Great, looking forward to your presentation. And Elizabeth also is one of our presenters.
Hi, yeah, I'm Elizabeth Yankovsky, and I'm a postdoc at New York University at the moment. I'm part of the climate process team on mesoscale ocean eddies. This is kind of a multi-institutional collaboration as well, and it's funded by NOAA and NSF with the aim of really parameterizing and developing parameterizations for eddies to be used in climate models that are at eddy permitting resolutions. And that's what I'll be speaking about today.
And David?
Sure. I'm Dave Bailey. I'm at the National Center for Atmospheric Research. I'm a community liaison for the Polar Climate Working Group. I also focus on sea ice model development and science questions surrounding sea ice and coupled climate.
Great, welcome. Michael?
Yeah, I'm Mike Spall from the Woodsole Oceanographic Institution, physical oceanographer. I'm interested in Arctic Ocean circulation dynamics. I live kind of on the idealized modeling end of the spectrum.
Great, welcome, Michael. Milena?
Yes, hi, this is Milena Veneziani. It's nice to be part of a small meeting today. I work with Wilbert and others within the climate group at the Los Alamos National Lab. I'm a physical oceanographer by training, and I mostly work on Earth system models. At least that's what I've been working on for the past 12 years or so, EGSM and other models.
Great to have you here. Gia?
I'm Jia Wang, ice climatologist at NOAA Great Lake Environmental Research Laboratory in Ann Arbor, Michigan here. I spent about 9 years at University of Alaska Fairbanks. I'm working both on Great Lake and Arctic climate change and coupled ice ocean modeling and nowcast forecast system.
Great, welcome. Thanks for joining. And Izu.
Okay, my name is Izu. I'm a grad student at the University of Florida. I'm interested in biogenic weathering and the feedback that like albedo that act in ice melt and deglaciation.
Great, welcome. Thanks so much for joining us today. And Devin.
Hi, everybody. Sorry for jumping on and off. I had some technical difficulties. So I sit in Vermont, but I'm actually an employee for Sandia National Laboratories, and I work on discrete element methods for sea ice dynamics.
Perfect. Thanks, welcome. And Wisla, we're just doing a quick round of introductions if you'd like to jump in.
Okay. Good afternoon, Wisław Masłowski, Naval Postgraduate School. work on the regional Arctic system model, modeling and forecast prediction, as well as jointly with colleagues at DOE labs on the Earth system modeled by DOE. Thank you.
Thanks for joining. Great to see some familiar faces and some new faces here as well. I will pass it over to Richard.
Hello. So our final 2022 modeling team meeting. So many of our meetings have focused on modeling applications. I think an aspect of today's meeting will focus a little bit more on modeling development, which I think is always a good idea to focus on that occasionally. So today we're going to take a look at a couple of aspects. One is scale-aware parameterizations. And Elizabeth will be talking about that for oceanographic modeling. And Lorenzo will be, I believe, will be talking about application of machine learning for sea ice modeling purposes. And in part, some of this work is affiliated with M2 Lines, which is a non-federal research initiative. So M2 Lines is sponsored by Schmidt Futures. That's a venture of Eric and Wendy Schmidt. I think Eric Schmidt used to be the CEO of Google. So the goal is to assess physical processes at the air-sea interface to reduce climate model biases and improve projections. So the other thing I wanted to say here at the introduction was that we're at the start of a new Arctic research plan. And there's also just been released a new biannual implementation plan. If you want to take a look at that on the IARPIC webpage, it's kind of intriguing about what program managers and Washington folks think are important topics for research that we should focus on. This meeting supports a couple of the points in the new plan to quantify and improve the predictive capabilities of Arctic models. And to support the Arctic component of Earth system predictability research and development strategic framework and roadmap. So this framework and roadmap document has several goals in it, one of which is to expand partnerships across disciplines with entities external to the federal government to accelerate progress. So we may talk a little bit more about that, but to start with, we'll start with Elizabeth's presentation. And do I have the title of your presentation? I don't. Elizabeth is from the Courant Institute of Mathematical Sciences at New York University. Her title is Modeling and Parameterizing Mesoscale Eddies in the Arctic Ocean.
Okay. Yeah, thank you very much for the introduction and also for the invitation to give a talk for this group. So yeah, my talk will be about modeling and parameterizing mesoscale eddies in the Arctic Ocean. I'll begin by speaking about one example of how mesoscale eddies, here I should say that when I refer to mesoscale, I'm referring to horizontal length scales of about 10 to 100 kilometers. So I'll be speaking about an example of how mesoscale eddies are really fundamental dynamical features that help shape properties in the Arctic Ocean. And then in the second part of my talk, I'll speak about some of my postdoctoral work in developing parameterizations for representing eddies in global climate models. So as some motivation, the Arctic, of course, is, as many of you know, very prominent in terms of how the shelf regions are very vast and make up about half of the total area. These vast continental shelves experience a very strong seasonal cycle with positive buoyancy forcing during the summer and spring months, and then during fall and winter, there is negative buoyancy forcing due to freezing ice and cooling, which leads to significant dense water formation in these areas. And so one of the kind of processes that I studied a lot in my PhD work was Arctic dense water formation. And in order to do this, I employed some idealized modeling. And the overall motivation for this is that Arctic dense water overflows, which is kind of the term for these dense flows that originate in the shelves and propagate into the interior Arctic. They are hypothesized to ventilate both the abyssal depths of the Arctic Ocean and also to maintain the halocline layer of the Arctic. And this is supported by some data from the 1980s, kind of shown here. This is from a paper by Egert et al. In 1981. Basically, in this paper, they were kind of showing evidence that in certain basins, such as the Canadian Basin, we see kind of very salty bodies of abyssal water. And the hypothesis that they kind of proposed is that these abyssal waters are actually sourced from dense shelf waters that make their way into the abyssal Arctic. On the other hand, kind of depending on the buoyancy forcing and the conditions of which these dense currents kind of form in, they can also maintain this cold halocline layer, which is important because it buffers the low salinity surface mixed layer from the warm Atlantic water that flows in beneath. So kind of understanding the dynamics of these overflows is a really crucial part of understanding the water mass structure of the Arctic Ocean. And so in my PhD work, as I mentioned, employed idealized modeling to study the dynamics of these dense Arctic overflows. This just shows kind of a schematic of what my idealized model looked like. It was based on having temperature and salinity stratification consistent with some observational data from the Kara and Barents Sea. And also the negative buoyancy forcing that I imposed was also consistent with some observations. And so basically I had this kind of setup, applied some negative buoyancy forcing over the shelf, and then investigated the dynamics of these dense waters as they propagate out of that shelf region and into the interior Arctic. So just to kind of give you a summary of what I found, the main result of this work was that mesoscale eddies are actually the process that initiates transport and mixing in these dense overflows. So here I'm showing two cases. One is kind of my nominal forcing case, which is consistent with relatively strong atmospheric cooling and also relatively vigorous sea ice formation with associated brine being rejected and causing waters to become denser. And then I also considered a weaker forcing case where the magnitude of the forcing was about 1/8 of this nominal case. And here what I'm showing is an isosurface of a tracer that was meant to track the dense shelf water that originated in the forcing region. And you can really see how there are kind of these eddy features that start to develop on the shelf region. And as these eddies reach the edge of the continental shelf or the shelf break, they initiate these cascades of dense water down the shelf. And then also kind of initiate some transport into the abyssal parts of the domain. If we have weaker forcing, we actually see that these eddies do not remain bottom intensified, but actually propagate into the intermediate layers of the Arctic. And so, yeah, this was kind of an interesting result because it's indicating that mesoscale eddies kind of initiate the transport of these dense waters, both into potentially the abyssal parts of the Arctic and also into some of the intermediate layers that can help maintain the halocline and some of the shallower layers. The other thing I looked at was the dynamics of some of the submesoscale instability. So in the bottom layer, or in the bottom two panels here, I'm showing in blue where the potential vorticity is negative. So that means that we have kind of submesoscale instabilities that are developing in these regions. So really the main message here is that mesoscale eddies are setting up these fronts that can then become unstable and lead to irreversible kind of shear-driven mixing. So based on this kind of sets up the fact that in order to really get the water mass structure and dynamics of the Arctic correctly modeled, we really need to resolve eddy features. The problem is that many of our leading general circulation models and ocean models are presently being kind of run at resolutions that are only marginally resolving eddies. So here I'm showing an important length scale that can be used to characterize whether or not we resolve eddies, which is the first baroclinic deformation radius. And basically the isoline here, where this is 2, means that we have 2 model grid points per deformation radius, which is kind of like the minimum requirement for even marginally resolving eddies. And you can see here that it's really only the low latitudes that are able to marginally resolve eddies. And all of the higher latitude regions, particularly the Arctic Ocean, it's kind of in this regime where we're not resolving the important length scales for capturing baroclinic eddies. And so this really motivates kind of the issue of parameterization in these regions. And so during my postdoc, I joined the Eddy Energy Climate Process Team. This is a picture of all of us during our yearly meeting in Boulder. And the goal of this group is basically to vet, improve, and unify new advances in energy, flow, and scale-aware eddy parameterizations. And as I mentioned, really, the high latitude regions are particularly problematic because we have smaller scale instabilities evolving in those latitudes, and also because these regions are very dynamic and are some of the most rapidly changing regions on our planet. So it's really important to model kind of the eddy processes at those locations, and it really poses significant challenges as well. So the tool that we've developed in the climate process team is an idealized model hierarchy to try to kind of get at the eddy closure problem a little bit better. So this is a one basin stacked shallow water configuration of MOM6, which is developed in NOAA GFDL. And the nice thing about this kind of idealized model hierarchy is that it provides a test bed for testing and developing eddy closures. It really allows you to look at eddy closures in the context of different resolutions and really kind of develop and test new ideas in a cohesive manner. So here I'm showing the 4 resolutions that make up kind of the basic version of this model hierarchy. And I'm showing the same metric, which is the deformation radius divided by the grid spacing. Basically, we consider kind of the 1/4 degree resolution as the lowest resolution of this hierarchy, and the truth kind of resolution that we compare our lower resolution runs against is a 1/32 degree model. You can see that it basically resolves the deformation scale at all latitudes reasonably well. And I also would like to point out that this 1/4 degree idealized model is actually relatively consistent with what like a realistic ocean model would look like. Okay, so now I'd like to speak a little bit more about the approach that I've been using to develop these parameterizations of mesoscale eddies. So this is an energetic approach, which was first proposed kind of by various groups, but in the most recent form that I've been applying by Janssen et al. In 2019. And the idea of this approach is really to parameterize the energetics of unresolved eddies. So if we look at kind of the overall energy cycle of the ocean, we can imagine it as having 2 large-scale reservoirs of potential energy and kinetic energy. These 2 reservoirs interact with each other through the overturning circulation and also through resolved mesoscale eddies, which kind of in a first order sense serve to extract potential energy and convert this to kinetic energy. These large scale reservoirs are maintained by buoyancy forcing, wind stress, and also dissipation. So then we can imagine in a model that does not fully resolve eddies, we have this unresolved eddy kinetic energy reservoir. This unresolved eddy kinetic energy reservoir actually interacts with both of the large scale potential energy and kinetic energy reservoirs. So there's a traditional parameterization, which is kind of the Gent-McWilliams parameterization for eddies, which basically parameterizes this component of this unresolved energy cycle. So it's the extraction of potential energy by eddies. And this is traditionally formulated as a buoyancy closure. Something that I've been working on is really looking at the kinetic energy or the momentum component of unresolved eddies. So I've been looking at something that's known as a backscatter scheme, which the idea of it is to re-inject some of the unresolved eddy kinetic energy back into the flow and energize the flow in a scale-aware manner. Notice that in this parameterization, we also have subgrid scale advection of energy and subgrid scale dissipation of energy. So basically, the way that this parameterization works is that we have a budget for the unresolved kinetic energy that we solve at every time step, and use this to inform the large scale energy, potential energy, and kinetic energy structure. So yeah, my work, as I mentioned, really focuses on parameterizing the momentum effects. And one of the questions that I've been asking is whether we can achieve the correct buoyancy structure by properly parameterizing the eddy momentum fluxes alone. So this is really applicable for kind of an eddy permitting model. I'm kind of arguing that maybe we can get rid of this buoyancy parameterization and just rely on kind of the momentum closure, and that if we do this in a physical and scale-aware manner, that we can actually get the buoyancy structure to be correct without actually having to parameterize it. explicitly. And just kind of to show you some basic results of this work, here I'm showing some snapshots of the vorticity and then the barotropic baroclinic kinetic energy time series. So these are just kind of two components of the kinetic energy. The barotropic kinetic energy is the part that's uniform with depth. The baroclinic one is the one that varies with depth. And also kind of a modal decomposition of the kinetic energy based on vertical modes. And the main takeaway from this is that we have kind of an unparameterized half-degree case here, and then we have the truth case here. So first, I attempted to test kind of the existing approach, which is to use the buoyancy closure only, and then combine the buoyancy closure with the backscatter or the momentum closure. And the main issue with both of these cases is that the fact that we have this GM or buoyancy closure, it actually double counts some of the processes that are actually being resolved already by the eddies that we have in the simulation. And so it really kind of points to the fact that we shouldn't be relying on this buoyancy closure at all, and we should really be focusing explicitly on the momentum component. You can see that this buoyancy closure kind of smears out some of the gradients and really kills off the eddies that we already have that are barely being resolved. And when we incorporate the momentum closure on top of that, it doesn't really help the simulation. It really is kind of dominated by this buoyancy closure. So now here I'm showing a situation in which I completely turn off the buoyancy closure and only use the momentum closure. And you can see here that our simulation is now much more energetic. So it basically has energies that are comparable with the truth case. And also the vorticity field looks much more physical and much more like the truth case. Even the vertical structure of the kinetic energy, when we look at the modal decomposition, it looks somewhat similar to the high resolution truth case. The only problem here is that we're actually have a little bit too much energy in the zeroth mode, which is actually the barotropic uniform with depth mode, which is shown in blue here. So this is indicating that kind of this basic approach for the backscatter is not entirely correct. It's kind of injecting too much energy into the part of the flow that's uniform with depth. And I'm actually in the process of using other types of physically based vertical modes to better correct for this problem. And I've been having a lot of luck with having kind of a backscatter that decays with depth. So that tends to kind of perform very well in actually capturing the vertical structure of the unresolved eddy energy really well. So I'll stop here. I basically just kind of want to summarize what I discussed. First, I showed that mesoscale eddies are a key process in dense overflow dynamics in the Arctic Ocean, really kind of motivating the fact that we need to be mindful of resolving eddies because they really play an important role in setting the water mass structure in this region. Then I discussed how parameterizing eddies at eddy permitting resolutions really poses significant challenges, particularly in the polar regions. And I discussed my work on developing a momentum-based backscatter closure through the use of an idealized modeling framework. And just a couple of points for discussion. Maybe we can think about how we can validate some of these parameterizations in a more realistic model. So as I said, I've been kind of looking mostly at an idealized modeling framework, but I'm thinking about incorporating this into a realistic GCM and trying to really evaluate how this parameterization performs there, which will be really interesting to see also how it interacts with sea ice and kind of other features that we find in a realistic GCM. And other thing that I'm really excited about is potentially using regional modeling as a tool for better studying some of these dynamics, because ultimately, as I mentioned, in kind of a quarter-degree ocean model, we're really not resolving the important dynamics. And regional modeling, I think, could be a really powerful tool to better addressing some of these mesoscale and submesoscale turbulence questions in the Arctic. So I'll stop there, and thank you very much for your attention.
Thanks very much, Elizabeth. So you're affiliated with M2 Lines, but this work is associated with your group. Who is the funder for that?
So the funder of this project is NOAA and NSF. It's jointly funded by both. Yeah. Mm-hmm.
Okay, great.
So we have collaborators actually at NCAR and at GFDL as well. Yeah. Okay.
And the highest resolution, the truth simulations, what was the resolution of those again?
The resolution of those was 1/32nd degree. So we saw some convergence between the 16th of a degree, which was the second highest, and the 1/32nd degree. So we kind of stopped at that point. Yeah.
So 1/32 is, what is that? That's like
Yeah, I mean, at the
2
equator.
kilometers?
Yeah, like three kilometers or so at the
3
equator.
kilometers.
So it's pretty high resolution. I should also mention that this model is adiabatic, so it has no submesoscale dynamics. It's purely like a kind of eddying model because we really wanted to study mesoscale eddies, which are to first order adiabatic. So
Right.
it kind of makes it a little bit easier to converge without having submesoscale dynamics there.
Okay, but that was a global simulation, was it?
So that was our idealized. It's kind of a one basin. It goes from -70 to +70. It's just kind of representing the Atlantic, but it's not yet a global simulation. I think that's kind of the next step is I'm going to try implementing this backscatter momentum closure in a quarter-degree ocean model.
Okay, wow. Dave, you have a question?
Yeah, Rich kind of stole my question, but that's fine. So, so your true simulation 1/32. I mean, I guess there's still potentially even some eddies where you're not quite resolving, like I guess you're getting more into the sub-mesoscale, and Baylor was in the picture there.
Yeah.
So, I mean, I guess in terms of the scale aware part of this, when does it start? When does it stop? I think because that's the biggest question about getting this in a big global model is understanding how you transition from one region to another. And yeah,
that's a really good point. Something that I didn't mention is that there's actually a resolution function in all of these closures, which looks exactly at that term that I was showing, which is the deformation scale. And the resolution function works so that as soon as you resolve the deformation scale, you tune down like the Jen-McWilliams parameterization, for example. Right now, the way that it's done in the default version of MOM6, the resolution function is the same for the backscatter and for the buoyancy Jen-McWilliams parts. And I kind of don't agree with that. So it's something that I'm actively testing. I really think that we need to kind of modify that scale awareness so that it really prefers the backscatter when we're at these marginally eddy resolving cases and relies more on the buoyancy closure when we're not resolving the deformation scale. Yeah, but it's definitely like an active thing that I'm looking into.
Okay, Gia, you have a question?
Yes, balconic instability usually occur along jet stream and crucial as a main. So this should have a vertical shear to produce the balconic instability, which is the force mode. So I look at your figure, and your mesoscale eddy everywhere. So I mean, maybe the parameterization impose too much. This kind of the parameter, this kind of the mesoscale eddy or something like that. But usually it occur on the jet stream or this kind of they need a vertical shear to make it.
Yeah, I think let me share my screen again. So in the truth case, I do think we have a bit of a Western boundary current that we develop, even though this is an idealized model. And again, it's only forced by wind. So there are no like diabatic processes here. But you can see in our truth case, we have a bit of a Western boundary current. And in our parameterized backscatter case, there's still kind of a higher intensity of eddy activity in this Western boundary current region. I guess your argument is maybe we're over parameterizing eddies in the interior ocean where there's less shear. Is that what you were suggesting?
Yes, that. However, if you look the whole entire domain, it's everywhere. So yeah. I wonder, is the parameterization too strong to make everywhere have a mesoscale eddy?
Mm-hmm. Yeah, it's true. It might be. I think that part of the issue is that right now it's just based on the velocity field of the model. So the way that the backscatter is formulated, the way that this backscatter term is formulated is that it's an anti-viscosity. So it's based on having nu, which is your viscosity coefficient, times the Laplacian of the velocity field.
Right, you are the horizontal.
Yeah, the
there's a
horizontal.
barotropic. But
Yeah.
I mean, most of it due to the baroclinic, which is a
Mhm.
vertical shear.
Yeah, exactly. So that's something that I've been modifying, is that I've been imposing like a first baroclinic modal structure onto the backscatter, which partially helps solve this problem. And it's something that I'm actively working on. I just didn't have the time to talk about that in this talk. But I agree with you that the vertical structure is like one of the most important components of this. And if you do not get the vertical structure correct, then the backscatter behaves in very unphysical ways. It removes too much potential energy and it over-energizes the barotropic mode, as you said.
Thank you.
And Michael Spall?
Yeah, I'm just curious, the Jen McWilliams and I think your backscatter parameterizations are both local in the
Mhm.
sense that they just depend on local
Yeah.
gradients of the large scale or the mean flow. Are
Yeah.
you able to evaluate from the 1/32nd degree model whether that's a good assumption? How far are eddies propagating from where they're formed to where they decay?
Yeah, that's a good question. It's not something that I have done yet, but I think it's something that we could evaluate in using the high resolution case. There is actually a transport term that we can turn on in this budget, which would move away some of that unresolved eddy kinetic energy into other parts of the domain, which that could kind of take into account some of this non-locality in terms of how we reinject the energy. But it's not something that I've played around with. Yeah, it's a good point though.
Okay, thanks.
Okay, quickly, Wilbert?
Yeah, quickly, just as a practical question about the implementation. So this adds one additional equation to the equation set, basically,
Yeah.
three-dimensional, and how expensive is that to add that to a general circulation model, for instance?
Yeah, so this is actually, yeah, two-dimensional. And like the tests that I've done with this parameterization, they really don't modify the expense of running the simulation by much. It's using things that are already kind of computed in various parts of at least MOM6. And yeah, I think it's very inexpensive. I think if you were to make it three-dimensional, then it would be a huge expense. But in this kind of two-dimensional framework, it doesn't add much expense.
So it's two-dimensional, even though you have a multi-layer stacked shallow water model, right? Is that what you're?
Yeah, so the model itself is three-dimensional, and we're solving the equations, yeah, for every layer. But the energy, this let me just show you again. This equation for the unresolved eddy kinetic energy, this E is kind of a depth integrated quantity. So this equation itself is two-dimensional, but when you kind of represent its effect on the large scale resolved flow, then you could have like a three-dimensional effect in the sense that, again, like this E is two-dimensional and all of these terms are two-dimensional, but this E kind of defines what your actual backscatter value is. So basically we use this E to solve for the anti-viscosity, and then the anti-viscosity is just the Laplacian, acting on the Laplacian of the horizontal velocity field, which is three-dimensional, like it has a depth dimension to it. So we're just using this and solving it as a two-dimensional quantity, but we're getting parameters such as kappa GM or the anti-viscosity that then interact with the 3D flow. Does that make sense?
A little bit, yes. Very exciting work. Thank you very much for presenting it.
Yeah, thank you for the questions.
Thanks, Elizabeth. That was great. Let's quickly go to our second speaker then. Lorenzo Zampieri is from the National Center for Atmospheric Research in Boulder. And he'll be talking about on the design strategy of subgrid parameterizations in modern sea ice models.
Thank you. Thank you for inviting me. Yes, I will talk about the design of subgrid parameterizations. And I want to start from this animation that shows basically the model output from a very high resolution model, I guess a couple of kilometers. And you can see the ice, the forming, cracks, openings. And today we will not focus on these aspects. We will just pick one pixel of this image, and we will focus on what happens at much smaller scales, so the order of meters to 100 meters. So yes, let's start by understanding where do we stand with current parameterizations at the subgrid scale. So in this sketch, I'm representing a bit the state-of-the-art parameterization in the IcePack model, which is the single column model used in the CICE model and in the CSM merge system model. You can see that typically the ice is subdivided in multiple thickness classes. They can be 5, they can be more. And this represents the heterogeneity of the sea ice at the subgrid scale. Then we also subdivide vertically the ice in multiple layers and also the snow on top. And each one of these layers has internal energy. And that basically defines a prognostic temperature profile inside the ice. We also have a prognostic salinity profile because the salinity can change. Then we represent in a quite good way the interaction of the surface with the radiation. We have representations of melt bonds and a few more processes, but these are the main one. And now the question is, where are we going next? So what's missing? And processes that are not represented in models currently are snow metamorphism and redistribution on different ice types. And then also we don't have an heterogeneous sea ice and snow density. We just have one constant value for the ice and one constant value for the snow. And the same is true for the conductivity. We just pick one value for the ice and one for the snow, even though we know that these parameters are quite heterogeneous. And yeah, this is a complex problem because there are a lot of interdependencies. We cannot really just tackle one of these problems. For example, the density of the snow depends on its evolution in time. And then the conductivity also depends on the density, but the evolution of the snow depends on the thermodynamics. So yeah, it's a complex problem, and that's why we don't have a good solution to it at the moment. So what's holding us back? So first of all, there is a lack of observations, I would argue, and not necessarily that we don't have enough observations, but these are not equally distributed in space. So for example, we characterize very well what happens on landmass ice, but this might not be so applicable for the Central Arctic. Then there is a certain discrepancy between what's observed as a parameter, maybe in the lab, for example, the conductivity, and what then is used in the model. Even though they refer to the same quantities, the effect that we want in a model might be different. So they are not always compatible. I would also argue that there is a lack of prognostic sea ice density description in the models. And this is because it's difficult to adapt density, and then the thickness would depend on the density. So this is a limiting factor. There is also the unwillingness to introduce more variables which are not easily comparable with observations. And also there is a certain uncertainty about the effect of these parameterizations on the sea ice and on the polar climate. And I don't want to say that these new parameterizations might break the system, but rather that the effect might be small. So yeah, these are all issues that we need to live with. And I think in today's presentation, I will basically show our strategy to overcome this. And we start from the observations, because in our case, that's the best representation of the system that we have. High resolution models don't really tell us much. And in particular, I think the Mosaic expedition, which happened between 2019 and 2020, really brought us a step forward. Today, we'll focus on airborne observations. On one side, the freeboard measured with the laser scanner altimeter. And yeah, here you can see, just for reference, this is probably a scale of 1 kilometer. The resolution of this field is 0.5 meter. Here you can see the ship in the ice, and you can see a lot of heterogeneity. There are ridges, level ice, there are open leads. And on the other side, we also have, for the same image, we have surface temperature measured with an infrared camera. And here you can see the thermal signal of these open leads, or recently frozen leads that are much warmer than the surrounding ice. You can see also the thermal effect of refrozen leads, which are a bit warmer. Here you have the ship and the landing stripe close to the ship. This is just one flight. I will focus on this today, but we have at least 20 flights of this kind. Yeah, it's so this is a very cool data set. And just for who is not familiar, the freeboard is basically defined as a quantity. It's the distance between the surface of the ocean and the interface between the ice or snow and the atmosphere. So it's the height of the ice that emerges out of the water, and it's a good proxy for the sea ice thickness. So when we plot these two fields, the temperature in function of the freeboard, we see some weird things. For example, we see that the thicker ice is warmer than the thinner ice. This is very counterintuitive, and there is for sure something wrong. So we investigated it a bit, and we applied multiple corrections. So as a first step, we collocated the temperature and the freeboard features, and you can see now the situation looks a bit better. Then in the next step, we corrected the freeboard for issues generated by the helicopter flight. And here you can really see what we expect. So a clear dependency between temperature and freeboard. So the thinner the ice, the warmer it gets. So now let's think a bit with the model lens. So we are still looking at these observations, but let's see them how a sea ice model would see them. So typically we discretize the ice in ice thickness classes, but we can do the same basically with freeboard classes. So defining sort of a freeboard distribution. In this case, I'm showing 5 classes, and here the dashed lines are the boundaries of these classes. Each one occupies a certain fraction of the image, and it's defined by the sea ice concentration here. And then they will have a mean freeboard and color coding the temperature for each one of these classes from the observations. And you can see that there is not a lot of difference between the temperature on these different ice types, except maybe you can see this first one is a bit warmer, but I would say the situation is pretty flat. We can do one step forward, and we can ask, okay, given the observed freeboard, which equilibrium temperature would the thermodynamic model predict? And in this case, I'm using a simple zero-layer model. So we can resolve basically the surface energy balance because we have also atmospheric observations. And the result is this. So in this case, you can see the ice is much warmer. You still have the warm temperatures over the open leads, but then also the level ice tends to be warmer than before. So just for reference, this was the observation, and this is how the model thinks the situation should be. So there are large differences, and what's happening is that the model conducts too much heat through the ice, and hence the warmer temperatures. So yeah, let's go back to think as a model. We have here our observations. This is the model, and here we have the difference. And you can see that this difference is much larger for thin ice than it is for ridges, which are where we have a temperature which is much better and much more consistent with the observations. Now, how do we develop our parameterization? So I think the question that we need to answer is, can we alter the conductivity of the model for correcting this temperature error? So what conductivity correction should we apply in order to get rid of these biases? And there you can see for the zero-layer model, this correction to the conductivity flux. We are reducing the conductivity of the system quite a bit, and this brings us to match the observations. And that's basically how we design our parameterization. We of course can repeat the process for multiple flights. We can find the link between our model state and conductivity correction, and then we can use maybe a neural network or a functional relation as a correction model if this dependency is simple enough. The caveats are, of course, that the zero-layer model is very simple, and it's much simpler than what's implemented currently as thermodynamics. And it's also that what I presented here really lives in the freeboard space, so we don't have separate information for snow and sea ice. So this conductivity correction, it's just goes on one parameter, but in reality, it really encompasses the effects on many unresolved processes. This can be, for example, the fact that the snow is not equally distributed on top of each one of the thickness classes. It might depend on the fact that there are differences in snow density depending on the class that we are considering, and so on and so forth. So now the question is, okay, where is the machine learning part? What's the role of machine learning in this parameterization development? And yeah, a couple of slides on that. So first of all, just I picked this image so you can see how the sea ice looks like in reality, and this is from the same day that of the observations that I showed you before. But let's focus on the machine learning part. As I said, we can use machine learning at the end of our parameterization development to basically build the functional relation between our model state and the correction that we want to apply to some parameters. But we can also use machine learning to enhance the observations. And that's also what we are trying to do in parallel. So we are trying to develop machine learning retrieval for the sea ice and snow thickness, starting simply from the freeboard. So the idea is to use spatial distribution of freeboard, which has information on the snow and ice distribution. For example, it's able to tell us something about snow dunes, snow drifts, pressure ridges, and to take a machine learning algorithm that can learn these textures, dependencies, and connect them to snow and ice observations from transect data collected during mosaic. And yeah, I'm not going a lot into the detail, just that we start from stencils of the observations that I showed you before, something like 15 meters times 15 meters. And through a convolutional neural network, we try to predict from the freeboard the snow and ice thickness at the central point. And here you can see just some preliminary results. We have the truth, so the transect that was measured by someone really walking on the snow and measuring the ice and snow at these locations. And this is the prediction of our neural network. You can see that I would argue the ice is quite well predicted. We get the ridges in the right locations and with the right thickness mostly. And the snow, it's a bit less skillful, the prediction, but we capture interesting features. For example, the fact that the distribution of the snow is preferential on one side of ridges compared to the other. So in this case, on the left-hand side. And yeah, these are aspects that are really difficult to represent with analytical models, but that's where machine learning component can help us. So yeah, that's it. And it's just to clarify that machine learning can really be used at different steps of the development process and not just at the end when we define the parameterization that we bring in our model. So yeah, thank you very much, and I'm happy to take questions.
Thanks very much, Lorenzo. So the question that usually comes up with machine learning is the amount of data for training. So you were able to supply training based on the by cutting up each of these the tracks in the the scans into smaller bits. Then is that how it worked?
Yeah, exactly. So we have that's a good question. We definitely don't have enough training. So our labels, let's say, that's how they are called. So our truth is these transects that people walked on the ice, where we had the measurements of the ice thickness and of the snow thickness with high precision. And we don't really have enough of them. There are tricks to increase the size of your training dataset, for example, is to, since this is based on convolution, we can rotate the scene, and yeah, this helps a bit to increase. I think, yeah, we would like to have more data, but on the other side, we need to live with what we have. And this shows that there are predictive skills. So this prediction is for a transect that was not used for training, of course. So you see that there is some potential. Of course, yeah, we might not be perfect, and in particular for scenes that are not seen so much in the training data set, for example, on very thin ice, because people simply don't walk on thin ice, and that's why we don't have thin ice on transect. So we might come up with something different there, but yeah, at least for the level ice and for some of the ridges, we have good data, I think.
Is there a length scale for ice conductivity, and is that a concern in the training?
Yeah, I mean, so for the moment, the conductivity is not used in a machine learning application, so I cannot really talk about training yet. But definitely the conductivity can change quite a bit, not only spatially, but also vertically. And I think the connectivity of the ice, it's quite okay. It doesn't change so much. What really changes a lot is the conductivity on the snow, depending on how compressed the different snow layers are. Then this really has a big effect on the conductivity of, for example, if we have dunes on the ice, then the difference from where we have a maximum and the minimum will be large. But yeah, we are trying to avoid really to deal with this very complex problem, because and just to have a sort of pragmatic parameterization that tries to take into account of the effect without really modeling all these very complex processes, for example, the snow metamorphism, and which require a prognostic density description that we don't have at the moment.
It's certainly a good reminder that there are some fantastic data sets that came out of Mosaic that can be used for these kinds of things. Are there any other questions for Lorenzo? Yeah, Dave, go ahead.
Well, I already know Lorenzo, what Lorenzo's working on, but on your point about the snow metamorphosis and the snow redistribution, I mean, E3SM and CSM, I mean, we're definitely working on that in terms of the new advanced snow physics that's going on in both models. So I guess what aspect of that are you thinking about in terms of building on?
Yeah, that's a good question. I think, yeah, there is so some work has definitely been done in redistributing snow from one thickness class to the other. I think what's really not there yet is also capturing the fact that, for example, when we have ridges, we typically have the preferential accumulation of the snow just on one side of the ridge and not on the other side. And since the heat fluxes are then nonlinear, then this also have an additional effect, for example. So I think that these details are still missing. We can shuffle snow, but still we don't have any information about the heterogeneity of the snow inside each separate thickness class. And I think that's missing. And also about the metamorphism of the snow, I don't really know how far it gets. So if it's just metamorphism then constrain the radiative part of the model, so the albedo, or if it's really a metamorphism that then we can use also for constraining the thermodynamic processes. So yeah, that's something that I still don't fully understand. Yeah.
Gia?
Two questions. One is are there any data point limit for the machine learning to derive a model or the results? And second is the machine learning derived from region A can apply to region B, which is there's no data over there.
Yeah, that's what we hope. And I think we need to contextualize a bit. So we are sure that this type of retrieval will not be perfect. So this machine learning model will have some extrapolation issues for sure. But right now, the errors that we see in typical CI thickness retrieval are anyway very, very large. So I think for ISO2, we have something like half a meter or more with the latitude dependence. So yeah, we can, even if we are not perfect, we can definitely improve on these methods, at least at this small scale. And we can, the nice aspect is that we can predict separately the ice and snow thickness, whereas with other retrieval method, we typically focus either on the ice thickness or on the snow thickness, and we model the other component to then apply the hydrostatic balance. So this is a nice advantage in this case. Yeah, but yeah, of course, I mean, there will be a certain there will be an uncertainty. I think right now for the ice, we have a 15 centimeter uncertainty. For the snow, we have a 6 centimeter uncertainty, which is, yeah, it's basically 20% of the typical snow thickness that we observe over the ice.
Thank you.
If anyone has to run, it's now a minute past the top of the hour. I think we'll just go a few minutes over. So Lorenzo, was this work funded through M2 Lines?
Yeah, yes, this work was funded.
Can you say a little bit about how you became involved with M2 Lines?
Yeah, so I mean, it's my involvement, like the way it started, it's not very exciting. I just applied to a position that was open, funded by M2 Lines. So before that, I was working on CI's model development, understanding what complexity do we need in our CI's models, and then this fitted really well for my current position. I think at the beginning it was not clear that we would have taken this direction. So at the beginning we were hoping really to do much more with learning from high resolution models, but then we realized that so for example, what Elizabeth is doing, but then we realized that for CIs, we don't really have these processes parameterized correctly. So we can increase the resolution as much as we want, but the snow will not start flowing correctly from one thickness class to the other. And that's why we went for mosaic observations. But yeah, in the project, there are many different venues. So people working on ocean or on atmosphere are mostly learning from high resolution models, for example, trying to parameterize for the atmosphere, the convection, and for the ocean eddies. But then there are also people that try to learn from data simulation increments to do bias correction. And for the CIs, it's done for the CIs concentration, for example.
And are there any issues associated with sharing data that's associated with the project or anything like that?
I think no. I'm sharing data among us or sharing data with the community, you mean?
with the community?
No, I think, yeah, we try to be pretty open. Of course, for example, these observations that I'm using for Mosaic, then the data policy is a bit more complicated because it was a big process, but they should become available soon. But I think the idea is to be open and really to generate training data set that then could live on the cloud. For example, we collaborate a lot with the PangeoForge project, and that can be openly downloaded and used also by other people for training. So yeah, there is really an emphasis of making this data set reusable also outside the project. I think that's the idea. Yeah.
Okay. Well, I'd like to thank you, Lorenzo and Elizabeth, for these great presentations.
Thank you.
There are no other questions. Again, we'll be on hiatus next month for our co-leads meeting to figure out what we're going to be doing next year with IARPC and our team. But I wish everyone happy holiday and a nice break if you have one coming up. And we'll see you again in the new year. So thanks very much, everyone.
Yes, great. Thanks. Very nice meeting.
Thank you.
Thank you. Bye.